Ever look at a complex aerospace part, maybe a turbine blade or a massive structural rib of an aircraft, and wonder, exactly how we carve those incredibly intricate shapes out of solid blocks of metal? I mean, we are talking about high-strength alloys being shaped with literal microscopic precision. How do we actually get from a raw, heavy billet to a finished, high-tolerance part without just melting it down and pouring it into a mold?
Well, welcome to This Explainer. Today, we're unlocking the secrets of what is arguably one of the most versatile and absolutely crucial manufacturing processes in the modern world. We're diving deep into the anatomy of milling. Think of this as the ultimate how-it's-made journey, where we take raw, stubborn material and systematically and pretty aggressively sculpt it into the complex parts that keep our world running. All right, here is our roadmap for today's deep dive. We'll start with 1. The magic of milling. 2. Peripheral milling explained. 3. Face milling operations. 4. End milling for complex shapes. 5. Mastering milling parameters. And finally, 6. The machines behind it all. Okay, let's jump right into section 1, the magic of milling. To really wrap our heads around how we shape these tough metals, we kind of have to zoom way into the micro level. What you're seeing is basically an army of single-point cutting tools working in perfect unison on a rotating cutter. Now, unlike a lathe, where you've got a single stationary tool peeling metal off a spinning part, milling flips the whole script. You've got this multi-tooth cutter bristling with hardened inserts. As it spins, every single tooth violently strikes the metal, shearing off a tiny chip in just a fraction of a second. It's a beautiful kind of chaos. So let's lock in exactly what we're talking about here. Milling is a highly versatile machining operation where a rotating multi-tooth cutter removes material while traveling along a specified path. Honestly, that path is the whole secret. Because the rotating tool is traveling across a stationary or maybe slowly moving part, it's not just stuck making round cylinders. It can carve out stepped cavities, splines, complex gears, and perfectly flat surfaces. Moving right along to section 2, peripheral milling explained. This is the first of our big 3 milling types, peripheral milling, where the cutter's axis of rotation is parallel to the surface it's cutting. Now, what's super fascinating here is the massive difference in force depending on which way the cutter rotates against the metal. Incline milling, or down milling, the cutter rotation physically shoves the workpiece downward. That pins the part down, which is awesome for flimsy pieces, but man, it starts with a huge impact on the tooth. On the flip side, you have conventional milling, or up milling. This actually tries to lift the workpiece up. But because the tooth starts its cut from the clean metal underneath and breaks out through the surface, it's way better for chewing through dirty, abrasive scale on forged metals without instantly ruining your cutter. If you look closely at these cutters, you'll spot a really specific design choice. You might be wondering, why not just use straight horizontal blades? Well, helical teeth, the ones with a twisted, spiral design, are overwhelmingly preferred. Because of that spiral, each tooth is always partially engaged with the metal. Instead of the whole blade just slamming into the metal all at once, it slices in progressively. That means way lower cutting force, lower torque, and a much smoother operation. Plus, it heavily reduces vibration, which machinists call chatter. And trust me, nobody on a shop floor likes chatter. All right, on to section 3, face milling operations. Now we hit the second of our big 3, face milling. Here, the spindle is oriented perpendicular to the surface being machined. Look at this thing just plowing through that aluminum workpiece, violently throwing chips everywhere. Because it's perpendicular, the teeth are cutting right on the face of the part. This actually leaves these really distinct, sweeping feed marks on the surface, kind of similar to what you'd see on a lathe. The final smoothness you get heavily depends on the exact corner geometry of the inserts clamped into that cutter body. But here's the really tricky part, how the tool actually enters and exits the metal. You have to optimize the life of those inserts, or they'll literally shatter mid-cut. If you increase the lead angle of the insert, you physically thin out the chip being carved away, which spreads the force out. But even more crucially, by angling the cutter relative to the edge of the metal, you make sure the very first impact happens away from the super fragile tip of the insert. Getting these geometry angles dialed in is the absolute secret to keeping your tools in one piece. Next up is section 4, end milling for complex shapes. The final of our big 3 is end milling, and honestly, the sheer variety of tools we have for this is staggering. This process gives us the ultimate versatility to cut out wild profiles, step out cavities, and drill right into deep pockets. Unlike face or peripheral mills, end mills actually cut on both their end and their cylindrical edges at the same time.
Check out the geometries. You've got straight flats for deep slotting, chamfers, and those fully rounded hemispherical ball noses. Those ball nose end mills are exactly what you use to trace back and forth to carve highly complex 3D sculptured surfaces, like massive steel forging dies. To really put the insane limits of these machines into perspective, just think about this number. 80,000. When we're machining massive monolithic aerospace aluminum components, modern end milling spindles can spin at an absolutely staggering 80,000 RPM. At those speeds, the machines actually need high-end hydrostatic or air bearings just to survive the forces. And honestly, just getting rid of the crazy volume of metal chips they spit out becomes a huge engineering challenge all on its own. Okay, time for some high-speed math. Section 5, Mastering Milling Parameters. So, we've seen the tools, but how do we know how fast we can chew through solid metal without blowing the whole setup apart? That brings us to MRR, the material removal rate. To figure out our efficiency, we combine 3 things in sequence. First, the depth of cut. How deep are we plunging? Second, the feed per tooth. Literally, how far the part moves forward for every single strike of a tooth. And finally, we multiply that by the spindle's raw rotational speed. Maximize those numbers safely, and your factory is highly profitable. Push them just a little too far and, well, things explode. And yeah, things definitely go wrong on the factory floor. When they do, operators use a cheat sheet kind of like this to quickly diagnose the issue. If a tool just straight up breaks, your parameters were probably too high or your angles were off. Run your hand over a part and feel a terribly rough finish? The feed was likely way too aggressive, or the metal actually welded itself to the cutting edge. And if you see those wavy chatter marks we mentioned earlier, that almost always means your machine or your clamps just aren't stiff enough to fight off the cutting forces. Finally, Section 6, the machines behind it all. You can't just have tools floating in space. You need the massive physical architecture of the machines themselves to provide the immense rigidity required here. But real quick, for the engineers watching, here are your rapid-fire best practices if you're designing parts to be milled. Don't design sharp internal 90-degree corners. Round tools literally cannot cut perfect internal squares. Prefer flat bevels over complex rounded radii. It saves a ton of tooling costs. And for the machinists, always mount your cutters as close to the spindle base as physically possible. Otherwise, your tool acts like a bending diving board under pressure, and you definitely don't want that. Back in the day, we did all of this on manual column and me machines. You literally had a machinist turning hand wheels to move the table in X, Y, and Z. But man, we have evolved. Today, it's all about massive, automated CNC machining centers. The peak of this tech are 5-axis machines. By seamlessly tilting and rotating the part while the tool is moving, they carve unbelievably complex, monolithic structures in a single setup. It basically takes human error completely out of the equation. I think this quote from our source material really hits the nail on the head for our journey today. Milling isn't just about cutting metal. It's the fundamental bridge between raw elements and advanced engineering. Honestly, understanding milling gives you the blueprint for understanding modern manufacturing, from the smartphone sitting in your pocket right now to the rockets we're sending into orbit. We've gone from simple hand-cranked flat cuts to 80,000 RPM 5-axis beasts sculpting aerospace titanium. So I'll leave you with this to chew on. As artificial intelligence starts designing structures that look way more like alien biology than traditional engineering, and as these multi-axis machines keep evolving, what impossible geometric shapes are we going to be milling next? Thanks for joining me for this explainer, and keep learning.